The next step in amplifier design is ensuring stability. There's no point in designing an amplifier with high gain if it's going to become unstable. So consider this representation of an active device. We have an input on the left-hand side here, and this will include the matching network. We have an output on the right-hand side, which will include the output matching network. So the active device itself is defined by its scattering parameters, and the input reflection coefficient looking into the active device will be affected by the output circuit, including the output matching network. There's also an input matching network. So gamma out, looking into the output of the active device, will be determined by the S parameters of the active device itself and the reflection coefficient looking into the input matching network from the active device. So now we need to consider how the amplifier could go unstable. So here is one scenario in which the amplifier could go unstable. Here we have a signal flow graph representation with the reflection coefficient looking into the input matching network from the active device, the reflection coefficient looking into the active device. Now if this loop here around the signal flow graph is greater than 1, has a magnitude greater than 1 and the phase is right, then there will be oscillation, because of course there will be some noise, always some noise. So a little bit of injection of noise into this feedback loop and the circuit could go unstable. So this amplifier could go unstable if the magnitude of gamma S times gamma in is greater than 1. Of course the phase must be correct, but we usually find that if the magnitude of gamma S times gamma in is greater than 1, then as the oscillations build up, or as the signal level builds up, the phases adjust. We do break into oscillation. We have a similar situation at the output. So the injection of noise into the signal flow graph with the loop formed by gamma out and gamma L can result in oscillation if gamma L times gamma out has a magnitude greater than 1. So here are our stability criteria. We must make sure that we do not have the situation where gamma S times gamma in is greater than 1, and we do not have the situation where gamma L times gamma out is greater than 1. So for stable amplification, gamma S times gamma in must have a magnitude that is less than 1 at all frequencies, not just at the 8 GHz frequency at which we're designing. We tend to have problems at low frequencies because gamma S times gamma in for a FET in particular tends to blow up at low frequencies. That is, it'll blow up if we don't take into account design. So gamma in certainly will go up because S11 goes up. So we have to make sure that gamma S becomes small enough that it suppresses oscillation. We must have a similar situation at the output. The magnitude of gamma L times gamma out must be less than 1 at all frequencies. Now, for passive sources and loads, we must have the magnitude of gamma S is less than 1 and the magnitude of gamma L less than 1. Now you may say, well, what situation do we have where we don't have a passive source and load? Well, it could be that we're looking into the output of a transistor in a previous stage, which could have a negative resistance, or we could be looking into the input of an amplifier which has a negative resistance. But generally we can be pretty sure that we're going to be in this situation. So if the magnitude of gamma S is less than 1 and the magnitude of gamma L is less than 1, the criterion for stability requires that the magnitude of the input reflection coefficient be less than 1 and the magnitude of the output reflection coefficient be less than 1. So have a look at our amplifier again. We have an active device here which has S parameters, and we can express gamma in terms of the S parameters of the active device and gamma out. And here is our expression here. So just the input reflection coefficient of a terminated 2-port. We can develop a similar expression for gamma out. So our amplifier is unstable if either of these conditions holds. If gamma S times gamma in is greater than 1, our amplifier is potentially unstable because of course the phase must be just right as well. But we can be pretty much assured that the phase will adjust. Even if we cannot be assured that it adjusts, we do not want to be in this situation and tempt fate. Similar expression at the output. So we have unconditional stability as long as the source and load are passive, that is, gamma S and gamma L have magnitudes both less than 1, if we have these conditions. So we have unconditional stability. It doesn't matter what our load is, what our source is, if gamma in is less than 1, and if gamma out has a magnitude that's less than 1. Now these are complex numbers. What's inside the absolute sign here is a complex number. The magnitudes of complex numbers on a complex plane describe circles. Formulas have been developed for stability circles, and by formulas for these circles we mean that we have formulas for the center and radius. So we can express amplifier stability on the complex plane. In this case we're using the Smith chart. That's the normal way we want to represent these numbers. So we're not talking about unconditional stability here. Unconditional stability means stable no matter what the load and what the source are. These are representations of stability for variable source and load. So first of all, these are the output stability circles, and they're on the gamma L plane. If S11 is less than 1, that is, if we're looking into the input of our active device and the S11 has a magnitude that is less than 1, this shaded region is our stable region. Gamma in has a magnitude that's less than 1 in this stable region, and in this circle, the circle itself is called the stability circle, inside the circle our amplifier will become unstable. So just considering the output of our circuit, we must make sure that gamma L, the reflection coefficient looking into the output matching network, is only in this shaded region and never goes into that unshaded region. So we can design an amplifier to be stable even if it is not unconditionally stable. If it was unconditionally stable, this circle would be outside the unit circle of the Smith chart. We have a dual situation when the magnitude of S11 is greater than 1, but tell you what, that doesn't often happen. A manufacturer of transistors really wouldn't be able to sell their transistor if the magnitude of S11 was greater than 1, because the transistor itself would tend to break into oscillation internally. Now we need to talk a little bit about CAD programs, because of course CAD programs don't want to use shading. It would become overly complex if we had shading. So instead, a dashed line is used to indicate the unstable region on a Smith chart. So we draw the circle. Of course this arc here is part of a circle which has a very big radius and the center is a long way out. The unstable region is indicated by the dashed line. And if the whole amplifier is stable, no matter what the load reflection coefficient is, well, we'll just draw a circle around the Smith chart and put a dashed line on the outside. So that's what a computer program does. So let's look at our particular amplifier. We want to design our amplifier at 8 gigahertz. And what we see here is that the entire Smith chart is stable. So our amplifier will be stable at 8 gigahertz no matter what gain. So our amplifier will be stable at 8 gigahertz no matter what our load is. These are output stability circles, so these circles are talking about the load reflection coefficient looking into the output matching network. But look here at 1 gigahertz. At 1 gigahertz, we must be careful as to what loads we apply to our circuit, because there is an unstable region up here. Now, what this is telling us is that everything below this line is a capacitor, so if the reflection coefficient looking in to the matching network from the active device looks like a capacitor, then our circuit will be stable. We would like our active device to see a resistance outside the amplifier region, just to make absolutely sure that things are stable. When we go up to 16 gigahertz, so we're at a much higher frequency, way above our passband, we see that there is another unstable region. So some capacitive loads will result in instability, and yes, if it looks like a short circuit, so if we're looking from the active device into the input matching network, if we see a short circuit there, well, then it will be unstable. But if we provide a resistive load, it'll tend to be stable, and of course if it's an open circuit, it will be stable as well. So we need to make sure that when we choose a matching network, that the matching network has this behavior, that at low frequencies we're in this region, and at high frequencies we're in this region. So we cannot just pick any matching network, we must make sure the matching network falls into these regions, and if the two element matching network that we're trying to design does not ensure this, we're going to have to add another element. At 8 GHz we don't have a problem, but at 1 GHz we must make sure that our input matching network ensures that gamma S is in the shaded region. So if it's capacitive down here, no problems. If we have a resistive load, no problem. But we need to be concerned if we see an inductance looking into the input matching network from the active device. Similarly here we see that we could go unstable at 16 GHz if we present something like an open circuit, or if we present, what would this be? This would be a capacitive element, very small capacitor that tends to look like an open circuit. Now, we usually like to design amplifiers to be unconditionally stable. No matter what happens, we want to make sure the circuit is stable. So our previous discussion refers to ensuring stability when we are at low frequencies and at high frequencies. The amplifier that we're designing with, the active device we're designing with, will be stable at 8 GHz, no matter what the input and output matching networks will be, but we need to pay particular attention at low frequencies and at high frequencies. So here are our two situations of stability. There's conditional stability, that means our load or perhaps our source reflection coefficients must be in the shaded region. Unconditional stability is indicated here, where the unstable region is outside the unit circle. We like that situation if we can achieve that, and this is the situation we have at 8 GHz. So rather than looking at a graph to determine whether we have unconditional stability, a couple of metrics have been developed. The first metric that was widely used is called the K-factor, or Rowlett stability criterion. And the K-factor is developed here, or derived here, for the active device at many frequencies. And what we need with the Rowlett stability criterion is that we need K to be greater than 1 for stability, and we also need the determinant of the S parameters, the S parameter matrix, to be less than 1. And so in this region between 5 and 11 GHz we see that we have K greater than 1 and we have the determinant less than 1. So between 5 and 11 GHz our amplifier using this active device will be unconditionally stable no matter what. There's another stable region at 22 GHz and above. At these high frequencies our field effect transistor has lots of capacitive parasitics internally, and those capacitive parasitics are shorting out our circuit. So we usually find with an active device that it's going to be stable at fairly high frequencies, but we're probably not going to get useful gain out of this device at those high frequencies. But at low frequencies and this mid-range frequency we can have instabilities, and we saw that with our stability circles as well. So it's unconditionally stable between 5 and 11 GHz and at 22 GHz and above, but below 5 GHz and between 12 and 21 GHz we need to pay particular attention to make sure that the amplifier we design is stable. Now, one of the things that is not so nice about this stability criterion is that we must use two measures, K and delta, and the relative level of K does not tell us very much. So K being large in the middle here is not telling us that our amplifier is going to be more stable. Well, since this K factor was developed, another factor has been developed called the Edward-Sinsky stability criterion, or the mu factor. Now, a CAD program will report both the K factor and the mu factor. Older books on amplifier design will only talk about the K factor, but the mu factor is much better. We can get rid of the K factor completely. Now, the mu factor is defined as the distance from the origin of the Smith chart to the closest point on the stability circle. Now we have a formula for the stability circle, and we're on a complex plane, so it's not surprising that we can come up with a formula for mu. And here's the formula for mu. The S parameters here are the S parameters of the active device. Delta is the determinant of the S parameter matrix. Now for stability, we want the distance between the origin and the closest point on the stability circle to be greater than 1. Because if mu is greater than 1, that means that our unstable region is outside the unit circle. So we no longer need to use two factors that the Rowlett stability criterion gave us. We just need the mu factor. And as well, if mu is much greater than 1, our amplifier is going to be more stable because our unstable region is going to be even further from the unit circle. So let's look at determination of the mu factor for our field effect transistor. So we want mu greater than 1 for unconditional stability, and greater mu is the more stable our design. So again we see that our stable region is between 5 and 11 gigahertz and at 22 gigahertz and above. And this is exactly what we saw with the K factor. The big difference is that we only have one factor to consider now, and the relative level of mu tells us how stable our design is going to be. So our design is going to be very stable in this 8, 9, 10 gigahertz region. We're going to be on the edge of unconditional stability between 4 and 5 gigahertz and 11 and 12 gigahertz. We're going to make sure that the right impedance values are going to be presented to the input of our active device below 5 gigahertz and between 12 and 21 gigahertz. Now, a CAD program can also report two levels of mu factor. Now, the mu factor that we talked about before considers unconditional stability at both the input and output. CAD programs report mu1, or what are called mu1 and mu2, where mu1 only considers the input stability circles and mu2 only considers the output stability circles. So this provides an indication of where the stability issues are going to be. Are they at the input or at the output? We're going to see that if mu1 is telling us that the input network results in instabilities, well, we'll also have an instability at the output. But the relative levels can be used. In this case, this is saying that if we consider just mu1 at the input, that our circuit is going to be a little bit more stable at 9 gigahertz due to the input than at the output. So this would tell us that maybe we want to apply a little bit more attention to the output network. Not a really big deal, but CAD programs do tell us both. So let's summarize where we've been. If an amplifier is unconditionally stable, design is considerably simplified. Even if an amplifier is not unconditionally stable, it could still be stable. Design is then tricky and is only done in special circumstances. So we saw with our transistor and the design we want to do at 8 gigahertz that it is unconditionally stable at 8 gigahertz. We have some issues at lower frequencies and below 5 gigahertz and at frequencies above 11 gigahertz. But we're not trying to design our amplifier to have good gain there. We don't care if we just simply suppress gain altogether. But at 8 gigahertz, our active device will result in unconditional stability. We should qualify that a little bit. If we used feedback, we could of course create an oscillator. What we have considered here is the active device on its own without feedback. So if we do not apply external feedback, at 8 gigahertz our amplifier will be unconditionally stable no matter what we do to the input and output matching networks. Now sometimes we must design amplifiers that are not unconditionally stable. This often happens at very high frequencies. To increase our chances of being stable, high frequency design always uses Class A amplifier design. By high frequency design, I mean design at maybe 20 gigahertz and above. Consider the design of an amplifier at lower frequencies. Now a cell phone manufacturer will design a power amplifier at the output of the cell phone. That power amplifier must be unconditionally stable because the loading conditions are a little bit out of the manufacturer's control. So what happens when a person covers the antenna by their hand? What happens if the phone is placed on a metal surface? If the phone is placed on a metal surface with the antenna directly against the metal surface, the output load is going to look like a short circuit. We need to make absolutely sure the cell phone is stable, that the amplifier does not break into oscillation. There's a severe price to pay if the amplifier goes unstable. In a communication system, if the amplifier goes unstable, the whole EM spectrum could be polluted. The amplifier could self-destruct, there could be thermal runaway. And in the agreements that cell phone manufacturers make with the service provider, there are dollar penalties to be paid if the amplifier goes unstable in a cell phone. Because from the cell phone vendor's point of view, that phone is going to take down the whole network, and that phone is going to have to be tracked down, and that could be a very expensive operation. So the penalties, both from the performance perspective, the performance of the system perspective, and from the perspective of the penalties that a manufacturer has to pay, are so high that we absolutely must design for unconditional stability if at all possible.